Twice, yes.
We need to talk about medians. That's it.
That's what we're going to do. And that's half.
Oh, okay.
Because it says medians and altitudes. So talking about 5, 4.
So we talked about med.
So a median, okay, so what we have to do is we have to, again, if you remember back to talking about mid-segments, we said they were mid-segments of triangles because there may be mid-segments of other shapes. Same thing for median. Median of a triangle, because we may talk about medians of other shapes. Okay? But a median of a triangle is a segment whose endpoints are a vertex and then the midpoint of the opposite side. Okay. As we kind of march through this chapter, we're going to have basically a lot of segments. We've already seen perpendicular bisectors. We've already seen angle bisectors. Now we're going to talk about medians. And then tomorrow we'll talk about altitudes. Okay? And by themselves, individually, these segments are not hard to recognize. They're not hard to remember. They're not hard to use and develop relationships with. But collectively, if I give you, like on a test, and there's, maybe 8 questions on a test, and 2 of them are median questions, 2 of them are altitude questions, 2 of them are perpendicular bisector questions, 2 of them are angle bisector questions, and they're all intermixed and intermingled with one another, then it's hard to keep track of what's going on. Does that make sense?
Look at the median.
Okay.
It looks like an angle bisector.
It does, and sometimes it is. And that's another thing that is problematic, okay? But we go off the definitions, we go off the information being provided in the picture, and I can tell you right now that because of the information being given, I know that median is not an angle bisector. Because there's no marks up in the angles that I think may be congruent. Does that make sense? Okay, so we need to know our definitions real well so that we can differentiate in our images what segments are medians, what segments are angle bisectors, which ones are perpendicular bisectors, which ones are altitudes. Okay.
So a bisector is only when they're equal on both sides?
Yeah. So an angle bisector is going to be something like if that's my angle, then I would tell you something like that.
So on tests, so they always show the angles congruent, or they always have the marking?
Yes. Okay, so this question says, based on the criteria provided in the picture, identify what point M is called. So what we have to do is we have to look at all these segments or lines that are creating M. Okay, so M obviously being this point right here, right? Okay, so that is being created by that right there. What is, based off the criteria provided and the information provided in the picture, that is a what type of segment or line?
What is it? Oh my gosh.
It's perpendicular, and these are both 7, so it's a perpendicular bisector. Okay, what is this that also is helping make M? Another perpendicular bisector. So off of what we learned in the last couple of days, that point is called a what? Circumcenter. Okay. Now point X, what kind of segments are making point X? That's an angle bisector and that's an angle bisector, right? So that then is a end center. Okay. Go to that's really the same question. I don't know if I've got another. Here's another one.
I got a question.
Yes.
Are all the notes, can you still print them out?
Yeah. Yep. Here, let's say that I want to look at point X. Okay. And I want to ask, okay, look at the segments that intersect to make that. This is one of those segments, right?
Yeah.
Okay. Is it perpendicular?
Yes.
It's a bisector. I agree with that because it comes at the midpoint, but is there a right angle marking here? No, so it's not a perpendicular bisector. Is it a angle bisector? No, these angles look like they're congruent, right? But one might be 44 degrees and one might be 45 degrees, or one might be 30 degrees and one 31 degrees, right? I don't know that. So there's no markings here. So the only thing that we have here is a segment that starts at a vertex and goes to a midpoint. So that is a median. Does that make sense?
Yeah.
X is also made by that right there,
Another median.
which is another median. So that is, we haven't talked about this point yet, but we would be, once we know what point is made by two medians intersecting, that's how we would identify that point. But the markings here would tell me that it's not angle bisectors that are making it. It's not perpendicular bisectors that are making it. Does that kind of make sense? So just want to make sure that we understand that is a point of discussion that a lot of, in previous years, people have struggled with because they go off of what it looks like instead of what information is being given.
I think that point from the two medians crossing is gonna be like so you can draw another circle.
It is not going to allow us to draw another circle, but it does provide us some interesting information. Okay, when we draw, so every triangle has three medians. Okay, all of those medians are going to be concurrent. They're all going to match up or meet up at one point. Okay, that one point is called the centroid. Okay, so we read the paragraph at the bottom there. It says, in a triangle, the point of concurrency of the medians is the centroid. Okay, and one of the nice features of that right now, like it's got a, so you talked about the circumcenter being able to draw the circumscribed circle, the incenter being able to draw the inscribed circle. There is a feature here about the centroid that is nice, and the feature is, it is what we call the center of gravity of a triangle. So if I were to ask you to take your desktop and give you a, like a jigsaw and ask you to cut a triangle out of your desktop, okay? Any triangle you want. And then I ask you to balance that triangle on the tip of a needle. You would have to place that needle at the centroid of your triangle. Does that make sense? So if I have a square, let's think about this. Got open GeoGebra. And I'll go back to that if you haven't finished writing that. But if I have something just like a regular polygon, so here's a square. If I want, and I cut that out of some material, let's say I cut that out of like plywood or something like that, and I wanted to, for whatever reason, balance that so that it was parallel to the ground on my finger or a needle or whatever, okay? Where do you think you would place your finger or your needle or whatever for that square?
Right in the middle.
Okay, so you would do that at the center of that square, where the diagonals cross, right? Okay. Now you would do the same thing if it was a rectangle.
Yeah.
Okay. If we had something like a pentagon, you would still, a regular pentagon, you would put it there, right?
Yeah.
Okay. But what would you do if your polygon was that? Where would you put the needle to balance that?
It would have been almost at edge.
You would put it so that's a median, and that's a median, right? You would put it, you only need two because all three are going to, so if I do that, that's going to be the third one, right? So you would need to put your needle right there. Is that cool?
Yeah.
All right, so that's called the balance point or the center of gravity, and we call that the centroid. Okay, so in regards to finding the centroid, okay.
Wait, can you go
Oh, sorry.
to the, do we need to know that theorem?
Eventually,
So should I write it there?
not yet.
Okay.
Which one?
The one on the board.
There's three.
So if you remember yesterday, we went through that long algebraic process of finding the circumcenter, right? Okay, writing equations, of lines, all that kind of stuff. We can do the same thing for any one of these triangles that we encounter for finding the centroid, because the median is you can find the equation for the median by taking the vertex that the median starts at, and you can find the midpoint of the opposite side, right? So when you have those 2 points, you should be able to find the slope between them, and then use one of them as x1, y1 to create the equation. And then we can go through that entire process that we went through yesterday to generate the ordered pair for the centroid, okay? However, and in the past I've shown this, and because they took our computers and re-imaged them, I had a program on my computer, it's about a $200 program from Maple, that we could do the algebra. It shows you, it does a lot of the algebra for us. But I wanted to demonstrate it on how doing that process will actually generate a alternative to coming up with the location of the centroid. And the location of the centroid, if I take any triangle that has an ordered pair of, let's just do it this way. Let's go A. This one will have an x value of B. This one will have an x value of C. And let's call this one D, and then E, and then F. So those are, remember, those are x and y values. Okay, so A might be 2, and D might be 5, and B might be 3, E might be -10, and C might be -12, and F might be 0. So those represent just real numbers, right? To find the centroid, and it's all, this formula is generated all through basically saying, okay, if I can find this midpoint right here, okay, so the midpoint right there would be C plus A over 2. Do you guys agree with that? Add the x's divided by 2. Add the y's divided by 2, so D plus F divided by 2. If I want to find that median right there, okay, I could find the slope by taking the y's, which would be E in D plus F over 2 and subtract them. And then take the x's of B and C plus A divided by 2, subtract those. Make all that one nice real convenient looking fraction. Combine my terms, all that kind of stuff. Common denominators, be real messy algebra. We can use that as our slope, and then we can use this point as x1 and y1, and we can actually come up with an equation of that dotted line. And that equation of that dotted line would have absolutely 0 specific numbers in it. They would have your numbers B, E, C, A, D, and F. Okay? But if we did that, and then we could do that, and that program I was talking about would do a lot of that math for us. We could do that here and find that one. And if we have those two equations, we could set them equal to each other, and it would give me this point right here, which would be our centroid. Okay? And what we will find out is that that centroid, its location would be A plus B plus C divided by 3. And then the y value would be D plus E plus F divided by 3. And what does that mean? It means your centroid is found at the average of your x's, comma, the average of your y's. Add your x's together, divide by how many you have. Add your y's together, divide by how many you have. And that is so much more convenient, so much easier than actually writing equations. Does that make sense? Joel, your question? You good?
So you could just
Good.
do like A, B, and C, and then D, E, and F, and all divide that by 2,
Yep.
like off the bat?
Yep.
Or would you underline?
So you're saying take D divided by 3, take E divided by 3, take F divided by 3, and then add those together?
No, like add all of them together, like so you don't have to find the lines by like doing 2 at a time. Like you could just add them all together and find the centroid.
Yes. So let's look at this real quick. We could take, if I give you that there, that triangle, okay? Put the points in here, name and value, okay. So if that's the triangle I gave you, okay, without the formula that I just provided you, what you would need to do is that you would need to find this midpoint, and you would need to find that midpoint. And then once you did that, there's a median, right? And there's another median, correct? And what you would do is you would take these two equations. Maybe it makes more sense to leave it in standard form. You would take those two equations, use a system of equations, use elimination, probably the way they're set up, and you would be able to find where they cross. Does that make sense? Okay. And if you do that, that's fine. But you could also take the x values and add together. So you got 2 plus 2, or negative 2, plus 6. You'll divide that by 3. And then you'll take your y values, which are 3, negative 1, negative 4. You'll divide those by 3. Okay, so I got to put some extra parentheses around here. And when you do that, where does that point show up? Shows right there where those two lines intersected, right? So taking the x's of the vertices of your triangle, add them together, divide by 3. Take the y's of the vertices, add those together, divide by 3, and it will give you point F here, which is your centroid. Does that kind of make sense? Okay. Which algebraically is much more simplistic than any other process. If I look at my centroid and I start changing my triangle, so G is the centroid now, where is that centroid always located?
Or those two medians cross.
Right, and the medians are always, by definition, they have to be always passing through the center of the triangle, right? So your centroid is always on the interior of your triangle. And that should make sense. It's the balance point, right? It's the center of gravity. It has to be on the inside of it. But we've seen that the circumcenter can be outside, right? The incenter has always got to be inside, and the centroid is always going to be on the inside. But the circumcenter, that was the one that could start on the inside. If it's an acute triangle, it could be on the hypotenuse if it's a right triangle. It could be outside the triangle if it's obtuse. So that's one thing, one aspect of centroids that we deal with. Now, another feature, I'm going to keep point G on there. All I want to do right now is just look at some distances here. Let me get rid of the rounding here. That worked. All right. So G is the centroid, right? Okay, I just got rid of the other line that helped make it. I just want to look at G and its position compared to point B and point E. Okay? If I take, I'm going to find 3 distances here. I'm going to take the distance from B to G. I'm going to take the distance from G to E. Let's just look at those two right now. How do those two compare? Okay, so what we're seeing here, if I take GE, which is 2.19, and divide it by BG, which is 4.38, what Jagger's saying is that we see a 1/2 relationship, right? 0.5 relationship. This is 1/2 of that. Or this is, if I change the order of division, this one would be twice as big as that one, right? Is that the same, because remember, as I change this triangle, these two values are going to change. Does that make sense? And those two values were used inside that formula right there, correct? So if these two values are going to change, this formula is actually changing as well. But does the quotient ever change away from anything different than 0.5? No. So I get here we've got, 3.77 and 7.54. Those are different GEs and BGs, but their quotient is still 0.5. Okay? So that's a nice feature about a centroid. And what we find out is that the distance, this is the way I'm going to phrase this, the distance from the vertex to the centroid is twice as big as the distance from the centroid to the midpoint. Okay? Vertex to centroid is twice as big as centroid to midpoint. Another relationship that we see. Let's take, instead of looking at BG, let's look at, and this relationship comes just from that 1 to 2 relationship. Let's look at, and it might make more sense to color code these. If I look at that distance right there, so I'm gonna make that distance red. And then I look at this distance here, and we'll make it blue. Can you kind of see that the blue one is the entire median? It's still kind of a terrible, maybe red's not the best.
That's a thick blue.
Can you see that dotted blue there? Is that okay? Is it? What I'm trying to do is get you to visualize the entire median from B all the way to E, which is the dark blue one, and then from G to E, which is just that light blue dotted one, right? If I were to take those and divide them, GE divided by BE, GE divided by BE, you see right there, GE divided by BE, it is this number right here. It's 0.3333333333. What's 0.33333333 as a fraction?
1/3.
1/3. So what that's telling me is that this GE is 1/3 the entire median. Does that make sense? Which my hope is that makes sense to us, because if we go back to the idea that this one here if we go back to that one there compared to that one there, this is in a 1 to 2 relationship, right? Does that make sense, everybody? So that means that there's like a point right there that would allow this GE, if I cut and paste that GE, I could cut and paste that 3 different times here, right? So going down this entire median. So one of those distances compared to the entire thing would be 1 out of all 3 of them. Does that make sense? So if that's a 1 to 3 relationship, then we can also make the argument that this segment here, which we'll make light blue again, dotted. So now this is the longer segment. This is from the vertex to the centroid. So if I look at B to G divided by the entire median B to E, that should give me a 0.6 repeating. It's rounding it to 0.67, but that is 2/3. So this distance here is 2/3 the entire median. Is that all right with everybody? if you don't like those fractions, you can put them in the, here I've got GE over BE. So if I go BE over GE, most people like this one better because we could say that it's a 3-to-1 relationship. If I do this one, it's still going to be a fraction, but if I go, so BE compared to BG, BE compared to BG, instead of a 2-to-3, we now have a 3-to-2, which is a better decimal than 0.6 repeating. But you either get a 2-to-3, a 3-to-2, or a 1-to-3, 3-to-1, or a 1-to-2, 2-to-1 relationship based off of that centroid and its positioning. That kind of makes sense? So I'm going to let you write that down. That is exactly what all of that is encapsulated in this theorem here, the concurrency of medians theorem. And then we are going to actually practice that inside some specific problems. So these end up being the types of questions that generally get asked with centroids, okay? We've got, and I should probably write this, I didn't write this in the notes, but the idea here is that H and I are both midpoints. Therefore, M to I and L to H are all medians, okay? So I should have written that in words or maybe done something like this with notation to say that those are medians. Why do I need to know that those are medians? Because that tells me then X is what kind of point? It's the centroid, right? Okay. Now, so when we have a centroid, so these pictures will have always two medians drawn in. But the reason they have two medians is so that you can locate the centroid. You don't need both medians to actually do this problem. They're only asking me about, right now, MX and MI. They say nothing about H to L, right? So what I like to do is either redraw or cover up the median that they don't ask me about. So I'm just going to cover up that median right there, because I don't need it. The only reason that median was there was to accurately locate where X was on that blue line. Does that make sense? Okay. So now we have to identify the relationships between MX, XI, and MI. Okay. So I go back up and it says find MX. So that's what I'm looking for, MX. And I asked myself, okay, so I'm going to highlight MX. And I want to know, how does MX compare to the other segments that are the median or parts of the median? Okay? So I'm dealing with MX and I'm also dealing with MI. That's the other part that I'm dealing with. So I highlight that. And what it tells me is that I'm comparing the entire median, which is the blue segment there, to the part of the median that starts at the vertex and goes to the centroid. And going back to what we talked about in the GeoGebra and going back up to this here, okay, when you compare the entire median to this purple segment from the vertex to the centroid, that distance, MX, is, that's what equal sign means, right? MX, so that portion is 2/3 the entire median, which is MI. Okay. Sometimes I think it's important maybe to have a little, instead of having this phrase here, have a generic phrase, or even these phrases that came up from this theorem. Okay, because that can be maybe sometimes misleading or confusing, because later on we're going to change the letters. I like to write something like this. The vertex to centroid equals 2/3, and then I'll write median. So then all I've got to do, if I can remember that formula, all I've got to do is fill in, okay, what was the vertex of the centroid that they're talking about? And then what is the expression for the median? Okay. If they were asking about, let me just cut this picture out real quick. So that's the relationship that we'll use here in a moment to do that specific problem. But let's say that they were asking us to compare that distance to the entire median. That's the 1/3. So the way I would write this is I would say that the centroid to midpoint, spell midpoint, right? The centroid, which is x, to the midpoint, which is I, is 1/3 the entire median. And the last relationship would actually be to compare that blue part to the green part. So that would be vertex to centroid is, okay, how much bigger is this one compared to this green one? It's 2 times. Okay, or I could put the 1/2 in front and a 1 over here. So the vertex to centroid is twice as big as the centroid to midpoint. I think those, now obviously we don't in a mathematics field, we don't ever write things like that. We don't write equations like that or formulas like that. We use variables instead because it's more efficient, it's quicker, right? But that is exactly what the theorem that was in that yellow box that had that triangle picture with like C, D, E, and F and all those other letters on there. That is the same thing. I think that's more informative though. Would you agree with that? I think that's easier to find what they're talking about. So when we go back to our particular question and I highlight the things that they're talking about MX and MI. So those are the things I'm comparing. Well, that is, so MX is vertex to centroid. So that's dealing with that. And MI is the entire median. So I know for this particular problem, I'm going to use that formula. Okay? And that's exactly what we have here. MX, so vertex to centroid, that is MX. So that's why I wrote that there. Is, so that's my equal sign. And then my 2/3, and what's my median in this particular situation? The median, they're saying, is MI. Does that make sense to everybody? Okay. Now, the next step, you can do whenever you want to do it. I think it makes sense to do it now. I'm going to get rid of fractions. Because right there, that is the equation we're going to use. We have to substitute MX and MI that are provided up in the directions. But I'm going to get rid of fractions right now. What would I need to multiply everything by to get rid of fractions? 3. If I multiply everything by 3, I get 3 MX's, and I get 2 MI's. And all that means is if I were to take, I don't know if I can do this. If I were to take 3 MX's and put them end to end, that would be 3 MX's, right? And then take 2 MI's and put them end to end. What's that tell me about those two distances? They're equal, right? They're the same. Okay? So that is usually a better, maybe algebraic expression for us, or equation, I guess, for us to deal with because we don't have fractions. Now all I have to do, or all you have to do, is plug in now what mx is. Mx was 5x minus 6. And then plug in mi, which in this case was 5x plus 6. Is that now an equation that we can solve? That gets us back to our algebra. And what would you do first? Distribute, so you get 15x minus 18 equals 10x plus 12. I'm going to subtract 10x from both sides, so you get 5x minus 18 equals 12. Add 18 to both sides. 5x equals 30. X is 6, right? Okay. Now there's a lot of work to these problems. And my opinion is the more work involved, the more important it is then for me to check it. Okay. So what I'm going to do is I'm going to take that 6. I'm going to plug it back in here, which I have to do anyways because I want what mx is. If I plug 6 back in here, do I get 24? If I plug 6 back in here, do I get 36? Okay. How does 24 compare to 36? If I put division, what's that reduce to? Both divided by 12 gives me 2/3, right? Is that what we said we should get? That makes sense? If this whole thing is 36, if the whole thing is 36, and the blue portion is 24, what is this purple distance? 12. How does 24 and 12 compare to one another? 1 to 2 or 2 to 1, right? And that's the other relationship that we can see. How does 12 compare to 36?
It's 1/3.
It's 1/3. So when you're done, when you find all three values and you're done with this problem, all three of those distances, when you compare them in any order, you should get 2/3 or 1/3, or you get 3/2 or 3, depending on how you divide. Or you get 1/2 or get 2, depending on the order that you divide. Does that kind of make sense? So that's the check. I'm always looking, when I'm done, I plug back in, I'm always looking for one of those ratios. If I get one of those ratios, then the other three are going to be there as well. Okay, or the two, however many there are. We'll stop there today. Tomorrow, my goal is, or my plan is, just to go through another series of questions like that one. I think with these, the more practice that we get, the better we will obviously get at them.
So we're not going to do altitude tomorrow?
Probably won't get to altitudes tomorrow. Over here?
Yeah.
Yep.